Good morning and good afternoon, everyone. We're right at the top of the hour, so we'll go ahead and get started with our Webinar Wednesday. Welcome to ARA's Webinar Wednesday. I am Sri Rao, your moderator for today's webinar. The title of today's webinar is Risk Management for Infrastructure Geotechnical Features. Next slide, please. Let me start with a few housekeeping items. If you have an issue with your sound and you're using your computer speakers, please dial in using the phone. If you have any other issue other than your sound, please use the chat box button to send a message to the host. Next slide, please. If you have any questions, please click on the Q&A button and send your questions to the host and panelists, and we will address these in the Q&A session directly after the presentation. To view the presentation in full screen, at the top of your webinar settings, click on the down arrow, highlight, view, then choose fit to viewer or fit to width or whatever size you want, and you can see that on the screen, the options you have. Next slide, please. Just a reminder that to receive a 1-hour PDH certificate, you must attend the full 1-hour webinar, and I'll provide more information on that towards the end of the presentation. So now I'd like to introduce our presenter, Mr. Jerry DiMaggio. And for those of you who are regulars for our Webinar Wednesday, you probably realize Jerry is our usual host for Webinar Wednesday, but today he's been kind enough to present at the Webinar Wednesday himself, and as a result, I'm going to be hosting the webinar today. Jerry really needs no introduction. Most of the people on this call probably know Jerry, but for the 1 or 2 people who do not know Jerry, Jerry has more than 45 years of experience in civil engineering and heavy construction. He's internationally recognized for his contributions to design, construction, forensic assessment, and dispute resolution, and also innovation deployment. As a senior engineer at ARA, Jerry serves as a project manager and technical subject matter expert on a diverse suite of projects. He holds a bachelor's and master's degree in civil engineering and is a professional engineer in several trades, and is also a master trainer. He's provided consulting services on approximately 1,000 civil engineering, civil construction, and business-related projects in all 50 states throughout the Americas, several Middle Eastern countries, and Australia. He has presented hundreds of seminars and workshops. His technical area of specialty includes structural foundations, earth-retaining structures, ground improvement techniques, engineered earthworks, risk management, forensic engineering, dispute resolution for transportation, building and energy projects and programs. As you can see, that's a very, very broad area of expertise that Jerry brings to the table. He has participated in over 25 dispute resolution projects ranging from DRBs, mediations, arbitrations, and bench and jury trials in federal and state proceedings. Very, very extensive resume for over 45 years Jerry is providing. And now I'll turn the presentation over to my colleague and great friend, Jerry DiMaggio. Jerry?
Thank you, Sri. Long introduction. That's what happens when you're around working and you're a failure at retirement, I think. So good morning, good afternoon, extending that greeting to everyone, and thank you all for joining today. I would like to set the table with a few introductory remarks. The technical program will be about 40 minutes, and then we'll turn the program back over to Sri, and he'll go through Q&A and several other activities. First, I use the term geotechnical feature, and not everybody on this webinar, we do have a large group today, so over 350 sites, knows what a geotechnical feature is. So not an all-inclusive list by any means, but certainly some of the most common that you may individually associate with are those listed here. Let me also use this slide to set the table for really the connection, at least in terms of the webinar, between risk management, some of you are quite versed in that topic, and geotechnical features. And I'll just give a brief introduction to risk management. I'll focus on a select number of geotechnical features, and my objective is twofold. My objective is to focus on keeping you out of trouble. And that means forensic evaluations as well as dispute resolution matters, as Sri mentioned. Secondly is to stress the importance of two topics, which I see repeatedly as being problematic. And those two topics, and please remember these learning topics. One is the imperative importance of verbal and written communication. And second is the imperative importance on projects from planning through post-construction of documentation. Now I'll jump around a bit relative to the individual features. We'll get back to that. I'm going to speak for a moment relative to the Geocommunity, and you can interpret that in this first bullet as you see fit. It encompasses a broad group of folks, owners, contractors, consultants, and material suppliers. Generally, my perception, and these are my views, so you can feel free to disagree with my opinions based on your own experience, is that most of the Geocommunity feels that they have a good understanding of risk well, and they routinely apply some level of risk management. My observation is maybe that's true. I'm not sure if it is. And the reason I make that comment in the first bullet is the number of dispute matters that are in the industry and the frequent disappointments relative to both profit and revenue, to a lesser extent, geo-feature performance, and currently the excessive staff turnovers that we see across the community somewhat suggest to me that that may not be true in terms of the first bullet. Is it? I'm not sure. I do quite a bit of training, as Sri mentioned, in geotechnical topics as well as risk management, and it strikes me that often in risk management settings, be it either a training session or a demonstration project on a particular project or program, I often notice the scarcity of members of the Geocommunity participating in these activities, and I really have to scratch my head and wonder why that occurs. Now, for those of you not familiar with some of the terminology, and I'll be quite brief in this topic area, is the definition and quantification of risk. And I'll read a few select slides to you, but this is not one of them, so I'm encouraging you to read along with me. What is risk? And two bullets which define that. Most people on the second bullet have a connotation that risk is always a negative impact on some objective that we have. Risk may be negative, that's what we call a threat, or maybe positive, that's what we call an opportunity. The other important item is in this definition is that risk assessment is futuristic. So it may or may not occur, and based on our knowledge at a given period of time on a project program or at an organizational level, we're estimating what is the possibility of a threat or an opportunity. Now, you can end up with lots of risk on a project, and I'll use project generically rather than repeating program and organizational risk. How do we quantify them, and why do we quantify them? Not addressed in this particular slide. We quantify them because if we take a deep dive into risk management at a project level, it's not uncommon to identify threats and opportunities that might reach 60, 70, perhaps 100. And we don't have the resources nor the enthusiasm, perhaps, to evaluate all of those. So we quantify the risk based on two variables, the likelihood of occurrence and the consequences of the impact should that risk actually occur. Now, unfortunately, to the geotechnical community, risk attributed to geotechnical features are commonly represent the greatest source of risk on many, many infrastructure projects. There's some factual reasons why that occurs. Many of you know that. It's really related to uncertainty and the fact that we're dealing with Mother Nature. Now, in this presentation, I'm going to focus, and we have a laundry list of topic areas that I believe are common geo threats And I'm focusing here on this slide on the negative impacts. That's the risks that are threats. I'm going to focus on the left column in terms of the subsequent slides, not in necessarily that those in the right column are less important, but in the time allotted, we really can't address everything in depth. So I'll walk you through these in a fair amount of detail, some with one slide, some with a few slides. So as you always do, those of you who sat through my classes or my webinars previously, I'll focus on the high points. There'll be a bit of scolding, if I can use that word, relative to how we in the geotechnical community could do a better job to keep us out of trouble. Now, I mean that in a constructive and a positive sense, of course, when I use that word scolding. Now, excuse me, when we do evaluate the risk, in whether they be in geotechnical area or other areas, we always look for ways to handle the risk. And one way of handling the risk is through mitigation strategies. And I've listed a number of mitigation strategies on this slide. Those of you who have some familiarity with alternative technical concepts and alternative project delivery methods can relate to the first two. The transition to performance-based specifications as compared to means and method spec. The consistent and repeatable use of constructability, peer reviews, and value engineering reviews can help us out quite a bit. I use the word optimization, and some folks have a pushback on the word optimization in terms of design and construction. That's not necessarily compromising safety. It's not necessarily putting you at risk as a designer or a constructor. It's doing a better job of closing the gap between the state of the art and the state of the practice. Now, many of you work in the transportation community and have some familiarity with reliability-based design. And perhaps in the United States, the most well-known example of that is load resistance factor design. That is, however, not, however, the only method of reliability-based design. That allows us, reliability-based design, permits us and allows us to do a better job of assessing uncertainty. Now, the other mitigation area that, fortunately, over the last, I would say, 3 decades, is the evaluation of improved procedures for determining geomaterial parameters. And I'll focus on that a bit as we go forward. So to make a long story short, I babbled a bit on this slide. We have a number of mitigation tools. Now, we can mitigate a risk, or we can do other things with risk as we go forward. And those other things, a way of treating threats and opportunities that we identify in a risk management assessment, are often referred to as the A-TEAM acronym. And you see risk at the centerfold here. And we just spoke about mitigation. However, we can just accept the risk and incorporate that into the additional effects of those risks occurring. We could transfer the risk. One means of doing that is through perhaps a design-build contract, where we perhaps sometimes excessively try to transfer risk to a constructor. The term enhance is really only appropriate relative to opportunities, and what that means is we've got some, remember, likelihood that an opportunity might occur and we could reap the consequences or the benefits of that, but we may be able to do something that enhances the opportunity likelihood, and that's going to be obviously specifically focused on that particular opportunity, or we could avoid the threat. Now, what complicates our life today, and I've been in practice, as Sri mentioned, actually in excess of 45 years, and I want to use the example, and I could do similar example slides on different subject areas in geotechnical design and construction. But I want to focus on the changes that I've observed in the deep foundation area. And I'm covering a broad period, and my message here is that you don't necessarily have to be exposed to 50 years of experience, but you should have an appreciation for history, and you should have an appreciation of what's changed. All of the items that you see listed on this slide, and I'll cherry pick a few keywords for you as we go along, make geotechnical features much more complicated than they were years ago. And years ago allowed you to interpret that on your own. And if we focus on a few of these, the first one, load demand, performance requirements and constraints for deep foundation geotechnical features have grown enormously. That places a huge burden on the geotechnical designer and the construction. Pile materials, and I use the term pile generically, have increased in both strength, availability, and sizes. We think of drilled foundations. Largest one, a drill shaft I've ever worked on was 15 foot in diameter. The deepest shaft I've worked on was in excess of 300 feet. Those dwarf by orders of magnitude, that example, what one was accustomed to in state of practice some time ago. Frequency of testing and the types of testing available, fortunately, both in terms of load and integrity, have increased tremendously. And let me jump to the bottom. And you see that's all in bold and it's all in caps. Construction has become much more important and critical to the need for designers to be fully aware of equipment and means and methods in the execution of the designs that they prepare. The summation of these topics, specifically only the deep foundations, remember again, we can do this for a variety of topics, complicates the lives of those that are involved with projects enormously and allows, permits, results, and much more risk associated with the execution of geotechnical features in this area. Remember, this area is only an example. Well, what else has changed? And we'll walk along in this next sequence of slides through a couple of topics that really cause us to pause and think as we execute design and construction. Perhaps 15 years ago, the earliest twinkles in people's eye were noted on the term that you see here, geotechnical asset management. Now we hear asset management has been a buzzword and continues to be a buzzword for a long time. We've got that variety of geotechnical features, and I use specifically as an example, what's the service life design of an embankment or a rock cut? These are things, I would say, in my kind of hindsight view, prior to 15 years ago, no one ever thought about, and even in fact today, we would have extreme difficulty evaluating what the service life design of an embankment or a rock slope would be. And I suggest to you, it's a very, very, very long time, but that doesn't necessarily mean that we don't have to be proactive in terms of asset management. So what does asset management do to us relative to risk management? Depending on our obligations for the long-term performance of the geotechnical features, it causes us to think quite deeply and have quantification and qualifications and qualitative evaluations on the design and construction work that we execute. I mentioned project delivery methods. There is a move, certainly in the public sector, and it was preceded in the private sector in the United States, the transition from a traditional approach of delivery, which is design, bid, build, warm and comforting factor by many people. And a number of folks, and there's a variety of methods, you can see those listed here in the subsequent unbolded regular font that I've shown. There's a variety of methods. This is not an all-inclusive list. So what's the purpose of this slide? We're changing the way that we do business and the obligations associated with that change. Specific example, most of our national codes, guidelines, and reference documents have been prepared based on our enormous body of knowledge associated with the design, bid, build method of project delivery. Those references globally do not automatically translate when we use different alternative contract delivery methods. You can get yourself in quite a bit of trouble if you're not cognizant of that statement and you do due diligence to make sure that that transition for the reference, guideline, and code that you're applying is correctly in concert with the method of project delivery. Contracting documents. Well, those have changed over the last few decades, and I've had a blessed career in my long time of practice, and I've seen a lot of projects, as was mentioned at the beginning. It strikes me that what's occurred in the last few decades in particular is the length and the complexity of contracting documents have increased enormously, both length and complexity. To make matters worse, and I'm suggesting that's worth, a contract document for a major infrastructure project easily could exceed hundreds of pages. Does somebody read that? I hope to goodness somebody reads them before they sign on the dotted line, as this gentleman is doing. Often, however, the geotechnical featured discussions and the connotations and statements in those contract documents have not had the review in some cases, or the input in many cases, of geotechnical specialists, both from the design and the construction sides of the house. That creates, if things go awry, enormous liability, which is unnecessary for those dealing with the geotechnical features. So get involved, be inquisitive. If you're shunned the first time for being inquisitive, come back again and be a nuisance. You need to be involved. I use as an example of contracting documents, and you're all familiar that plans kind of go along with contracts. So as an example, on a driven pile project plan, it's not unreasonable to expect that all of the items listed on this slide would be somehow addressed in the plan notes or the plan sheets. That's a lot of territory to cover. It's easy to omit one or more. It's easy sometimes to have a disagreement between the geotechnical design reports that are finally approved and what's in the plans. And in many cases, in particular on alternative contract delivery projects, the geotechnical reports, i.e., are part of the contract documents. So conflicts between the geotechnical report and the plans will get you in trouble. You need to check. Make sure all these items as needed to be addressed are included. Again, just an example. Sticking with driven piles, let's focus on specifications. General statement is that specifications for all types of geotechnical features have become much more extensive. I recently was involved with the development of a special provision for a deep, large diameter drill shaft project. The length of that specification, I recognize this slide says driven piles, but the sections are all the same for all types of piles. The length of the specification for the project I'm referring to, and this is recent within the last 2 months, was 53 pages in length. Go back 2 decades ago and think what the length of a driven pile or a drill shaft specification would have looked like in terms of numbers of pages and the degree and extent of specificity. A lot of details need to be included and need to be complementary to each other on these types of projects. Again, why is that change? Because driven piles, drill shafts, all of the geotechnical features have become much more complex, as we previously mentioned. Now, I'll dwell a bit on the benefits of improved site characterizations. This is a focus area that traditionally, forgive me, big fingers there. Traditionally, we might have known this as geotechnical investigation or geotechnical exploration. The more appropriate and all-encompassing term is site characterization because it involves surface as well as subsurface data collection. It also involves office as well as field evaluation. So let's take a little look at why this topic is so important to capture. And frankly, site characterization, I'll use that term going forward, is often overlooked because we deal with that, unfortunately, as a commodity aspect of geotechnical design and construction. That by itself, that view, commodity aspect, low bid, will get you in trouble. Let's take a deeper look. First of all, you should be fully aware as a geotechnical specialist of the regulations and the legislation associated with differing site conditions. I don't have time, although we could take a deep dive into differing site conditions, type 1s, type 2, give you guidance in terms of how to proceed. But the bolded section here is highlighting that full disclosure of all factual information in contracting documents is imperative. That's a must. That's fundamental. But yet, often in disputes, we will find out that full disclosure has not occurred. The purpose of a differing site condition clause is intended to get contractors or bidders to limit their contingency regardless of the method that's used as a delivery method. Now, the first bullet refers to federal law, but we'll often find in practice that's recommended best practice, whatever best practice means, I'm not sure, that it appear in both public and private projects regardless of the funding mechanism. Soil mechanics and rock mechanics, part of site characterization, are pretty boring topics. In fact, the undergraduate class that most of the structural engineers that I know well took is the primary reason why they went on to specialize in structures. They were snoozing during soil mechanics and rock mechanics classes, simply not because of their skill set nor the instructor's capability, but this is boring junk. And if you pick up a book, if you're not into these topics, you would be mistakenly led to the fact that, gee, all soils fall into two categories. They're either coarse-grained or they're fine-grained, and that's dependent on some index values and some strength values. And you would be left with the wrong impression that this is pretty simple stuff, and it ain't. And if you don't get somebody working on your team who understands this like the back of their hand, you're going to get in a whole lot of trouble. Now, rock, I have to admit, in my career was a bit late in coming. Remember, 45 years, I had a lot of room to grow. Rock is much more complex material than soil, and we have rock which varies enormously in its engineering properties, and I'll pick on unconfined compressive strength because everybody's familiar with strength of concrete. By definition, an unconfined compressive strength of rock is any rock strength greater than 1,500 psi, and there are people that, because we haven't, as geotechnical specialists, educated them well, failed to recognize that beginning at 1,500 psi, rock in the continental United States can be as strong as 60,000 psi. That's quite a range. So understanding rock is very important for certain geotechnical features. And then the final statement relative to soil and rock mechanics, again, make sure somebody on your team knows this like the back of their hand. These textbooks that are written on a national or regional level can't possibly address all of the regional geomaterials because there's local geology and regional geology, and you need to understand that there are many deposits in the United States that don't neatly fit into our definitions by textbook of either soil or rock. And they're in-betweeners. Say, oh, that's very impressive, Jerry. So what has that got to do with the price of steak today at the supermarket? The importance of recognizing that is that the models that we use in the calculations for performance of both either soil and rock are not well suited to fit these regional geomaterials. And the term regional geomaterials has become more and more common, and some of you may be familiar with intermediate geomaterials, which was originally coined and has been replaced by this term somewhat. Both terms kind of focus on the same thing. Everything is not as simple as you think. So kind of to close this section out, what's the link between site characterization importance and risk? And there's no free lunch here. So if you're going to expend more effort, and I use the term effort, that could be resources by money or staff time, what you're trying to do is actually reduce threats, reduce the risk, and increase certainty. And if you look at the 4 bullets on this slide, they speak to more specific benefits of an adequate site characterization. There's an enormous amount of information that's available from FHWA, the Corps of Engineers, AASHTO, just to name a few, that addresses this topic. Now here's a conundrum. Because soil and rock is not man-made materials, we've got to be fully cognizant of the engineering property that affect our infrastructure feature, the geo feature. And I'm using as an example, one example, the evaluation of soil shear strength. And in slide 23, I've listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 fairly common methods to determine the shear strength of soil. Again, just picking this as an example. Which one is correct? Got an answer? They're all correct in certain specific sets of circumstances. Many of them, however, are incorrect for execution of design details and planning on evaluation of constructability. So it depends, a common answer to an engineering question if you're stumped to provide an answer to a colleague or a professor. Repeat again, all good tests, all give a good value, sometimes, depends on specifics. One of the things that feeds into the previous slide that's of importance are the items that are listed here. Again, focusing only on one engineering property. And in this particular case, the design value that we select has to match what we're going to construct and what we're designing for, rate of construction loading, direction of loading, levels of tolerable deformation on the facility we're building, and the influence of sequence and the means and methods of construction. So this is not done commodity evaluation by either laboratory or in situ tests. We're trying to model as best we can the engineering feature, the geotechnical feature that we have in mind, and we have to be fully cognizant of the load side of the equation, the serviceability in terms of level of deformation, and the execution of the construction both by means and methods in sequence. If we fail to do that, you just got a number. And it's probably the wrong number, wrong standard deviation removed from the mean. Not a man-made material. So often we forget the consideration of site variability, a topic which is of extreme importance and fortunately finally receiving due attention. This slide is taken from an FHWA document. What you're looking at, just to orient you, is measured and interpreted parameter values in the left column and the corresponding coefficient of variation range in the right column. The slide was assembled in a two-phase fashion, originally by Dr. Michael Duncan, preeminent professor at Berkeley and then Virginia Tech. And Dr. Duncan assembled a version of this table based on his evaluation of a number of case studies and looking at the properties, not all the case studies, at all the properties listed on the left column, but looking at the coefficient of variation for each of those case studies independently, and then the range of the coefficient of variation for the body, the population of properties that, case studies that he had. So let me give you an example. I got a little tongue-tied there. Undrained shear strength SMU. Dr. Duncan found out from the case studies that he examined that the coefficient of variation for only those case studies where S of U values were available, the COV between 13 and 40%. 40% COV is pretty scary. This table was then updated now some time ago as well by Federal Highway Administration with some additional case studies. Now, I leave this slide to your attention. The fact is that at a particular site, be it a vertical infrastructure for a building or a horizontal infrastructure for a railroad or a roadway, we may in fact have multiple sites that have to be evaluated based on some basic statistic evaluation, looking at mean, looking at standard deviation, looking at coefficient of variation. We may have more than one site. Just because it's a project from A to B doesn't mean it's one site. And then, even if it is one site, there's an inherent variability in the material. So there is guidance in AASHTO of how to select. AASHTO is the American Association of State Highway and Transportation Officials. The section is section 10.4 that I'm referencing of the bridge design specification, and it suggests the reasonable approach to the evaluation during the design phase of the project on how to select the geomaterial parameters. Now, historically, where have we goofed up here? We didn't follow this guidance. We gravitated, as a community, we gravitated to the lowest data point in the body of knowledge of the strength data that we had for a particular project. That's not appropriate. You do that historically when asked, why did you do that? The designer would robotically answer, it's a conservative approach. Well, it may not be the most conservative approach because the property that you pick might be an outlier. It might be unconservative. And if you're excessively overly conservative, you don't want to be there because you won't be called by the civil specialist, the structural specialist, the hydraulic specialist. Groundwater. We're almost near the end of this little segue. Groundwater is often a topic overlooked. We think that when we drill an exploration and we encounter the water table, that it's static and it goes down to infinity. If you think the geotechnical material environment is complex, you haven't lived until you've looked at hydrogeology and looking at the subsurface environment at some sites. It can be extremely complex, often overlooked in practice, often overlooked in terms of time changes, both in a calendar year or through multiple years through the duration of a project, looking at, for example, extreme events. Slope failures, right? I give you a few examples of deep foundations, but slope failures, be they either soil, as shown here, or they be rock, rockfall, or rock instabilities, are thousands. And I would say there's thousands on the highway system, let alone other infrastructure that we build. Well, what's changed over time? We've dealt with instabilities for quite a long time. What's changed is the sophistication, and this is a great enhancement, so it provided us a wonderful opportunity. And I'm showing you two graphics here, one a limited equilibrium analysis, LE, on the right, and then a finite difference analysis using a flat program. Excuse me, I said on the right, but I meant the left figure, LE, right figure, finite difference. These are fantastic. What we've forgotten, however, again, being enamored by beautiful graphics is wonderful, but what we've forgotten that strikes me is that we have not focused well, and we seem to have lost from the early 1970s, which was some of the earliest advent of use of computer programs and stability analysis, the importance of search routines, the importance of failure surface changes. Not everything is circular. Get that in your head and keep it there. It may get you into trouble if you forget that. Also, how to build a model from the geotechnical profile point of view. All of those things, I'd suggest to you, are more important than the output that we can get and the results from the output that we review. If we have garbage in, we have garbage out. I'm going to move along a little bit further. We're doing well on time. Now, moving back to deep foundations as an example, but now to the construction phase. One of the great innovations that we've experienced in the last few decades is the means by which we can evaluate the geotechnical capacity. In this particular situation, I'm looking at a variety of tools that are available today routinely, or often used routinely. Static load tests, dynamic measurements, wave equation computer analysis, dynamic formula, which may still be appropriate on smaller, simpler projects, and office static analysis. Now, we may have on some projects all 5 of these. Say, well, which one should we use? And probably everybody who has some familiarity with testing would say you obviously should place most credence with the static load test. That may be true if it's done correctly according to the ASTM standard procedures, and more importantly, interpreted correctly. However, the purpose of this slide is that with all 5 of these, if you indulge me, on a project, it is imperative that the specification specifically identify what is the basis of acceptance for the final pile. You say, well, doesn't it always? Most often it does not. Now, we have all these sophisticated tools, non-destructive testing methods. We could see in the ground and tell if it's going to rain tomorrow, not undermining the importance of those. However, often what we forget is the importance of the inspector. And I'm using the term inspector here because the individual roles and responsibilities would vary depending on the method of project delivery, between the owner's representative and the contractors. That inspector is the primary source of information as the execution of the work is ongoing. So make sure that the specification correctly identifies the whole enchilada in terms of the basis of acceptance. Don't use exclusively non-destructive testing methods as a basis of acceptance. Frankly, that's wrong. We seem to have learned, since the wave equation was developed over 70 years ago, the original computer model was developed, we seem to have learned the importance and the meaning of the word drivability and its limitations. Maybe we did, and you don't want, unfortunately, to a much lesser extent, we see the results of these exhumed piles that you see on the left and the right, respectively. However, we still seem to have a mentality on many projects to overdrive the pile, and to make it more insulting, to use something like the dynamic pile tester to verify the importance and the validity of what we're doing. So we use a very great, sophisticated tool, and then we hit the pile way too many times. It's very important that your acceptance procedures for any of the geotechnical projects explicitly define what is the driving criteria to be used as the basis of acceptance for the pile. That is imperative that you do that. There are explicit definitions of practical and absolute refusal, which should be followed. And as I've underlined in the header, these are unfortunately misapplied and misinterpreted in practice. And I give you guidance in this slide for future reference of the importance of that. This slide obviously goes along with the previous slide. Be explicit and be reasonable. We still, in some projects, be of the mentality for a driven foundation, the harder we hit the pile and the more often we hit the pile, the better the pile is. That is totally and absolutely 110% incorrect. Drill shaft inspection. Well, you see a couple of problematic shafts. I did not take either one of these slides here. And the problem, if it's not obvious to everybody, we should have some concrete cover that generally is between 3 to 6 inches, and perhaps in some cases a bit thicker than 6 inches, on the outside of the perimeter of the furthest outside reinforcing element, right? The hoop stresses or the loops. Now, why does this occur? Inadequate flow of concrete through tightly spaced reinforcement, poor concrete mix designs, and poor placement procedures. If we use the existing reference and guidance material that's available, these situations should not happen. Unfortunately, these situations still routinely occur. You get into disputes, you end up in dispute resolution, you don't want to be there. We have a number of tools that are available, fortunately for us, in non-destructive testing for both driven and drilled piles. See them listed here in terms of the three most common ones. You know each one: ultrasonic logging, thermal integrity profiling, and gamma-gamma. Each have a corresponding standard testing method, either by our friends at Caltrans or ASTM. Some basic description, if you're not familiar with the tool, and the primary application. Each of these tools has got a very defined role and has got significant limitations in application. None of these tools, as I mentioned previously, should be used as a basis of acceptance. Last comment. We seem to be tongue-tied in mixing up the three terms you see on this slide. What's a defect? What's a flaw? What's an anomaly? I have a problem with that word, as you can tell. These are all explicitly defined in ASTM D6760. They mean entirely different things. And just because you have the first two, either one, doesn't mean that the shaft needs to be, or the drilled-in-place pile, auger cast pile, micropile needs to be rejected, or remediation needs to be applied. A defect can be a geotechnical defect or a structural defect, and is only to be determined based on an evaluation by the structural or the geotechnical designers. Concrete is a special requirement for these. I've already talked about that. And there's many tools that are available to do an adequate job for inspecting drill shafts. Now, I already spoke about foundation acceptance. And the last slide, before I turn it over to my good friend and colleague Sri, is what we covered. Hopefully, the value to each of you was to talk about some geo threats and some mitigation procedures to avoid problems. So with that, I'd like to turn it back over to Sri.
Well, thank you very much, Jerry, for an enlightening presentation. For the participants, if you have any questions, please submit those now, and Jerry will answer as many as possible in the time available. We hope you enjoyed today's presentation and that you will join ARA for future webinars. You can see a couple of them listed. We have a full schedule of webinars for this upcoming winter. The two that are next are Kevin Elliott is going to present some communication tips for engineers and scientists, and I know I need that, Kevin. And then Carmen will present, Carmen Dwyer will present pavement marking, mobile reflectivity data collection, data applications, and collection applications and return on investment. So with that, can you move to the next slide, please? So let's get to the Q&A portion of this webinar. And Jerry, I have a few questions from participants, so I'm going to read them to you. So the first question comes from John, and he states, it appeared that you listed value engineering as both common geo threat and as a potential mitigation strategy. Please comment on the relationship between risk management and value engineering.
Yeah, Sri, I lost the audio for a second. Could you repeat that question?
Sorry, it appeared that you listed value engineering as both common geo threat and as a potential mitigation strategy. Please comment on the relationship between risk management and value engineering. Well,
yeah, that's a good question. So, I mean, value engineering is most typically, it's an old tool. It's not used as often as it used to be, but I would encourage on complex and not necessarily major, but complex projects to have some kind of a value engineering during the design phase. The design teams do a great job. But value engineering, for those that are not familiar with it, you bring some outside experts in that render some opinions of where there might be some risk exposure, or in fact some better ways that should be considered before the project goes to sale.
So, Jerry, here's another question. Do you have suggestions as to how the construction industry and geotechnical community can shift away from site characterization as a commodity?
Sri, I'm sorry, you're breaking up again on my end. Sorry.
Okay, let me repeat that. Do you have suggestions as to how the construction industry and geotechnical communities can shift away from site characterization as a commodity?
Yeah, that's a tough one. I think the word that comes to mind is to have respect for the importance and the risk that are associated with site characterization, because I think historically it's been relegated, with all due respect to those that do that important consideration of work, it's not tied to design and it's too fragmented. So I think of it holistically, and think of the value added is the two words that come to mind.
Thank you, Jerry. Here's a question from Jose, who states, what's your best advice for researchers looking for developing retaining wall deterioration models?
So I'm going to use my trump card and say it depends, Jose. It depends on what kind of retaining wall it is, and it depends on what the deterioration mechanism that you're evaluating. So if, for example, it was a mechanically stabilized earth wall, a reinforced stone wall that used metallic reinforcements, then the deterioration mechanism that most people are focused on would be corrosion. But that's only one deterioration, only one deterioration mechanism. So I go back to my short answer is, it really depends. You have to look at the wall, look at the permanent surface life requirements, and look at all the possible mechanisms that could adversely affect the performance of the wall.
Thank you. Here's a question from Michael. Where could I find some more information on when to use practical versus absolute refusal for a specific project?
Oh, well, thanks, Michael. That's an easy one. I would point you to two references. One combined reference is the AASHTO Bridge Design Manual, and I don't get rebates for selling these. The complementary manual is the AASHTO Construction Specifications, which are much less known in terms of practice. Then the second reference is Federal Highway Administration document, and the most recent edition is 2016, is Design and Construction of Driven Piles.
All right, thank you, Jerry. John has another question, and this one's a little forward-looking. It appears we are in a period of more extreme rainfall events or more frequent extreme events. Are you advising your clients differently with respect to design groundwater levels or scour risk?
I think again, that's a pretty general question. I would say my advice to the clients is to be more cognizant than perhaps most people have been historically on looking at extreme event effects and since you mentioned rainfall and we talk about scour, I mean, those of you not familiar with it, we're required by design to design for deep foundations for scour events from a 100-year storm, and then for an extreme event check to make sure we have life safety in hand, we check for 500-year storm. Having said that, Rita and Katrina were not 500-year storms nor 100-year storms. So that has to be looked at more extensively, because these features we're building have a design life of, it may be in excess of 100 years. Current guidance in AASHTO for a brand new highway tunnel, as an example, is a 150-year design life. So if anybody knows what's going to happen in 150 years, please write me a note. Yeah.
So Jerry, here's a question from Alex, and his question says, have design concepts and theories been able to keep up with the increasingly larger foundations that are routinely constructed? If not, what can be done to bridge the gap?
I don't think, the short answer, Alex, is yes. In my opinion, the design models have kept up. I don't think all the engineers have kept up, and you noted one of my bullets of what we could do is to move, to reduce the gap between state of art and state of practice. So I'm less worried about the models, and I'm more worried about kind of educating engineers and educating engineers who don't routinely work with geotechnical features every day of their lives. So that gap has to be narrowed. That's really the chore.
Jerry, here's a question from Aziz. His question says, for risks associated with pockets or seams occurring in the middle of layers like clay or sand, is there any way to mitigate that risk? Well,
I think the first thing is through site characterization is the fingerprint. Well, two answers quickly is, one is to understand geology if you anticipate that particular strata might be present. As a tool in siting characterization, the cone penetrometer with pore pressure transducers is an excellent tool to pick up these lenses and layers that are intermittent in a deposit. In terms of how you implement that and consider that in your design, it really depends on the feature that you're building. So that's the best I can do. And Sri will mention at the end, but you all see my email address, and I'll be delighted to provide responses to any follow-up questions anybody has.
Yeah, thank you, Jerry, for your responses and for the presentation. And thank you, everyone, for your questions. I did not get to all of the questions that we had in our Q&A pod, but as Jerry mentioned, you can send that questions to us, and you can send Jerry an email, and for the next 24 hours, and we can respond to your emails. We request you ask informational questions, not consulting questions, please go to the next slide, Jerry. So on behalf of ARA, thank you for joining us today. Today's presentation is being recorded, and a link will be made available on the ARA's Webinar Wednesday website, probably early next week. We will also send PDH certificates to all participants verified by our attendance report as present for the full hour of the webinar. A copy of today's presentation will also be included with that email. Please allow a couple of weeks to receive your presentation. Next slide, please. ARA is always looking for great people to join our team. If you're interested in employment opportunities at ARA Transportation Infrastructure Offices, please send a resume and contact information to www.joinara@ara.com. That's www as in Webinar Wednesday, joinara@ara.com. Thank you for joining us today. We hope you will join us on November 10th for our next Webinar Wednesday, which will be Communication Tips for Engineers and Scientists. Thank you, everyone, and have a great rest of the morning and afternoon.